Hello. In the previous video, we discussed a picture of linear algebra. And today, we study systems of linear equations. Before moving to a general case, let's consider some examples. The very first example is the equation of a straight line. We know that general form of the equation of straight lines looks like ax plus by equal to c, where a and b and c are real numbers, right? X and y are variables. Okay, so in order to solve this equation, we need to find all pairs of x and y satisfying this equation. That means when you plug x and y into the equation, you have the identity, right? Let's pick a concrete examples. Okay, so let's say if I have 3x plus 2y equal to 7, I need to find all pairs x and y. So how to do that? We have only one equation, right? And we know that on this straight line, there are infinitely many points. So we expect that the equation has infinitely many solutions. Okay, so I would choose x or y, right? And I express x or y via another variable. So let's say, let's solve this equation for y. And we have, this is just 2y equal to 7 minus 3x. I just subtract both sides by 3x. And then I divide both sides by 2. I get y equal to, let's say, negative 3 over 2x plus 7 over 2. Okay, so this is the y. How to write the general solution of this equation? I write in the following way. I have x, y right here, right? And we already fixed x, so we just replace the y with this, because y depends on x. So I have x negative 3 over 2x plus 7 over 2, and that is the general solution. That means each time when you give a value of x, you have a pair of points, right, on that straight line, or you have one solution of this equation. Does that make sense? So in general, I hope you still remember the equation of a plane. Okay, let's talk about plane. All right, so we have the second example right here. I have ax plus by plus cz equal to d. That is equation of plane. Okay, so if you give me four numbers a, b, c, and d, so I have some equation of plane. And of course, again, right, sometimes we need to describe all points on the plane. So how to do that? We do almost the same thing as in the previous example. Let's consider the following example. I pick just x plus 2y minus, 3z equal to, let's say 4, okay? Now we need to describe all points on this plane. Again, we have only one equation, so we need to pick just one variable. Let's say z, okay? Or maybe z is not good. I pick x. The reason I pick x because the coefficient here is just 1, so I don't have to divide anything like this. Okay, so I pick x. I have x equal to 4 minus 2y minus 3z. Okay, all points x and y, z on this plane can be rewritten in the form 4 minus 2y minus 3z. And then here I have y and z. You see that? So actually this is already, general form of the solution of this equation. or this is general form of poised on this plane. Okay, so we may look at this formula from different points of view. So what is that? So if you remember if you already took calculus 2, right? So you study surfaces, everything. We know we learn function of two variables in calculus 2, right? So this formula says, yeah, for each pair y and z, you have some point on the space, and that point can be described by this formula. Does that make sense? So this is some kind of function of two variables, and this describes some surface, and that surface is a plane in this case. Agree? So if you already took calculus 3, you probably know vector functions. So this is an example of vector functions. Okay, but that's about calculus. Now look at this from the point of view of linear algebra. So what is that? I may continue from this vector in the following way. I will separate y and z, okay, and the free coefficient right here. So I can write that is 4. In this, I don't have any free coefficient, so that means I have 0. Here, I also don't have any free coefficient, so I have 0. I just separate them, okay? Okay, next, I will separate the y in here, the y in here, and the z in here, and the z in here. So I write y right here, okay? For this y, the coefficient is -2. I write -2 in here. In here, I have coefficient 1. But in this term, I don't have any y. So that means, we have 0 in here, okay? Next, we move to z. I write z in here. In the first term, I have -3. So I write -3. In the second term, I don't have any z. I just write 0. In the next term right here, I have 1z. You see? I have 1z, so I write 1. Okay? It is interesting, right? So you can see, yeah, actually, the solution of this equation can be described as this, right? So all points like this, or can be described as a linear combination of these two vectors, and you move along some another vector. That is quite interesting. You see that? So, we will study in detail about linear combinations, everything else. But, sometimes we can describe a general solution of some linear equations like this. Make sense? Okay, let's look back again, right? In the first example, you consider some straight line. One linear equation in two variables. You have to pick one and express another via that one. So you got this, okay? Next, you have one equation in three variables. So your general solution depends on two variables. All right, so these two examples are very, very easy examples of a linear equation, and we just show that how to solve such linear equations. Okay, before we move to a system, so I would like to give you some examples, some equations that are not linear. This is not linear function. This is not linear because we have squaring here, right? Linear means the power is just 1, okay? This is not linear because we have exponential function in here, okay? This is not linear because we have sine x in here, okay? So, when we are talking about linear equations, means we have only degree 1 in here, just 1, nothing else, okay? No, we don't have any other functions, just polynomials, but degree just one. So you might have x, y, z, whatever you want, right? You might have many variables, but the degree here is just one. Don't forget that. All right, now let's talk about systems of linear equation. I think we already discussed about that in the very first example, but it's okay to repeat it again in here, right? So I remember we studied some system like this: x plus y equal to 1, and x, let's say, plus 3y equal to 5. Okay, so this is a equation of one straight line. We just talked about that, right? And this is another straight line. Solving this system means we need to find all pairs of x and y satisfying both equations. That means we just need to find the intersection of two straight lines. Let's consider another example. We have system of three equations in three variables: x minus 2y plus 3z equal to 9, negative x plus 3y equal to negative 4, and 2x minus 5y plus 6z equal to 10, for example, right? System of three linear equations in three variables. Okay, so we just discussed about this, right? If you have such equation, that is the equation of some plane, right? So basically you have three planes in here, and solving this system means you need to find the intersections, right, of three planes. Does that make sense? We might look at system of linear equations from different points of view, and one useful point of view is geometrical point of view. Okay, all right. Of course, you might have a system of millions of equations, right, and in billions of variables, but that's fine. In that case, we will not have straight line, we will not have plane, but we still have some system. Okay, all right. So we already discussed about how to rewrite such systems in the matrix form. Okay, but before that, I would like to give you a general form of a system, and then we will solve these two examples using matrix forms. Okay, all right, let's go back to the very first one. This is general form of a system. So suppose that you have n variables in here: x1, xn, and a11, a12, a1n are coefficients, and b1, b2, and bm are real numbers. So if you just compile all these equations together, you have a system of linear equations. That's it. All these are coefficients, and if you pay attention, we numerate 1 1 in here. What does mean 1 1? That means this coefficient is in the first equation and corresponding to the first variable, right? And what is a21? A12 is in the first equation and for the second variable. Similarly, okay, let's say a2n means on the second equation and for xn, right? In here we have m equations, so I have, for example, am1 means, in the m equation for the first variable, am2 is for the m equation for the second variable, and so on. So you have a system of linear equations. Okay, now let's go ahead to rewrite two systems in here in the matrix form before we solve them, right? So let me erase this. Now we will discuss just algebraically. I can rewrite this in the matrix form. I say, yeah, I pick the coefficient right here. I hope you still remember that, right? I have coefficient 1, 1 in here. Here I also have 1, and here I have 3, right? So I just pick 1 in here, another 1, and then B. B is free coefficient, right? And here I have 1, 3. Okay, and here I have 5. Okay, I remember we wrote this way times x and y, and then equal to 1, 5. Does that make sense? You know, it's pretty easy. You just pick coefficients, right, from the equation. So here I will write in short, the first row would be 1, -2, and 3. Okay. And here I have x, y, and z equal to 9, -4, and 10. Okay. In the second equation, I got -1, 3. Here we don't have any z. That means we have 0. And here I have 2, -5, and 6. So we already have, you know, matrix form of these two systems, right? And, you know, we might rewrite this in a shorter way. The way this. Here we have x and y. Here we have x, y, and z. But, you know, they are variables, right? And sometimes, you know, we don't need to write them in the system. So how to rewrite this? I will rewrite in the following way. I write 1, 1, 1, 3, and that is 1, 5. Okay. So, you know, I just ignore x and y because we can denote using another symbols. Is that correct? For the second one, I might write just 1, -2, 3, -1, 3, 0, 2, -5, 6. In here, I have 9, -4, and 10. That's it. So if you pay attention, what is 1, 1, 1 in this case? What is 1, 1, 1? 1, 1, 1 is from here. The coefficient 1, and 1 right here. Is that correct? So what is 1, 3, 5? 1, 3, 5 is right here, the second equation. So that makes sense, right? And then what you have in here, 1, -2, 3, 9. So I have 1, -2, 3, 9 right here. The second equation, -1, 3, 0, -4. -1, 3, 0, -4. Next one, 2, -5, 6, 10. I have 2, -5, 6, 10. So that's how we can convert a system of linear equations into matrix form. All right? All right. Now let's pick the first system and solve it. I will show you two different ways. The first way is with x and y. The second way is in this form, in the matrix form. Okay, so let me rewrite that. X plus y equal to 1, x plus 3y equal to 5. We need to solve these systems. We have two equations. I can denote by 1 and 2. Okay, and from 1, I have x equal to 1 minus y. Or you might write y equal to 1 minus x. That is your choice, okay? So you may express x via y or y via x. And then you plug this guy into the second one. So we just substitute, right? So that's why, you know, sometimes this method is called substitution. So, and then we substitute this into 2. We got, instead of x, I have 1 minus y, right? This is x plus 3y equal to 5, okay? And then we have 1 minus y plus 3y equal to 5. I will simplify y with 3y in here. I have 2y, and here I have 1 with the 5. So I simplify by 1. I got 4. And then from here, I got y equal to 4 over 2, which is 2. All right, we have y equal to 2. Now, in order to find x, we just plug this guy into this equation. You don't have to plug into the first one, right? Because you already solved for x right here. X equal to 1 minus y. So from here, we get, finally, we get x equal to 1 minus y, which is 1 minus 2 is -1. Okay? So the system has only one solution. -1 and 2. All right? So, this way is called substitution. So that means you have to pick one equation, one linear equation. You choose one variable, express and solve that equation for that variable. We already did that at the beginning of this video, how to solve a linear equation, and then you substitute that into the second equation. If you have more than two equations, you do almost the same thing. You pick the first equation, solve for some variable, plug that into other equations, and then you have a system of linear equations, but the number of variables is less than the number of variables in the original system. Okay, so now I will show you how to solve such system in the matrix form. Okay, so let me write here so you can compare, right, which method looks better. Okay, so the matrix form looks like 1 1 in here. I have 1 1 3. I have 5 in here. Okay, so what does mean substitution? Substitution means, I need to solve the first equation for some variable. I picked x in this case, right? I solve x equal to 1 minus y. And in the second equation, I plug this into the second, you see? Into the second. And in the second equation, I don't have x anymore. So that means I have to eliminate x, right? In the second equation. That is the key. I need to eliminate x in the second equation or y in the second equation. So I look at this. I have 1x in here. You see? I also have 1x in here. So I just subtract them. Does that make sense? Because I want to eliminate the x. So that means if I fix the x in the first equation, I don't want to see the x in the second. This coefficient should be 0. That's what I want. So the easiest way is I will multiply the first equation by -1, right? And add to the second. Does that make sense? So I can write in here just row 1 multiply with the negative, and then I add to the second row. Okay, I add to the second row. This is row 1 multiply with -1 plus row 2 add to the second row. Does that make sense? All right, let's try that. Okay, and we'll see. I fixed the first equation 1 1 1. So when I do this operation, I have to do that for all coefficients on each row. Okay, so 1 with -1 is -1. -1 add with the 1, I got 0 right here. Okay, now I pick 1. 1 with -1 is again -1 plus 3 is 2. You see that? And then -1 with 5 is 4. So that is my second equation. If you compare this with this guy, you can see actually they are the same. Why? 2y, this is 2y equal to 4. Look at that. But if you solve in the matrix form, it looks like, yeah, it's faster and Much easier. The idea is almost the same. The idea is you need to eliminate the x or the y in the second equation. So that's why I just multiply this by -1, add to this. I just want to make this guy become 0. That's it. Make sense? You know, you have another way to make that guy 0. You can just take the first equation and then subtract the second. But if you subtract, you will have the following one. I can write here, okay? I just take R1 minus R2, and I do that in the row R2, okay? And I have 1, 1, 1. The second one is 0. 1 subtract 3. Subtract by 3 is -2. And 1 subtract by 5 is -4. So again, you have -2y equal to -4. This is the same with this, with the negative only. You see, we have different ways to do that, okay? So from here, I will rewrite this equation as 2y equal to 4, and then I got y equal to 2, and then I plug y equal to 2 into the first equation, okay? So I got x plus y equal to 1, so x equal to 1 minus y is -1. All right, so you know, this is just another form of substitution. Okay, let's use this method to solve the second equation, but I will not solve in this form. I will use the matrix form. Agree? And then we finish today's lecture. Let me copy this. All right, let's solve this system. Now, I will fix the first row, okay? We fix the first row, and as we have seen that, we need to make all entries right here equal to 0, because we want to eliminate the x, right? So the x in the second and the third equation. Agree? This, you know, don't forget, the first column is about coefficients of x, this is coefficients of y, this is coefficients of z, and this is free variable, so I denote by b. Okay, let's do this. Now we have 1 right here, we have -1, so I just add them, right? I'll write in here R1 plus R2. We do that in R2, means row 1 plus row 2, and we do that in row 2. Okay, so I'll have 1, -2, 3, and 9 here, and here I have 0. You know, when I do this operation, I have to do for all entries, right, in each row. So 1 with -1 is 0, -2 with 3 is 1, 3 with 0 is 3, 9 with -4 is 5. Okay, so we can do that, you know, on row 3 at the same time. So we have 2 in here, we have 1 in here, so I will multiply R1 with -2. I add to R3, I will do that in R3. How about that? So in R3 I have 0 in here, and then -2 times -2 is 4. 4 plus -5 is -1. And then 3 with -2 is -6. 6 plus -6 plus 6 is 0. Wow, looks nice. And then 9 with -2 is -4. 18 plus 10 is -8. That's it. You see? So we have another system, right? Of course, you know, this system should have the same solutions as the first one has. But we don't have x and y in the second and the third equations. You see? Okay, now We don't care about the first equation. Now we care about this part only. This part. So we have system of two equations in two variables. Solving this system, and then we plug this back here, we can find the x. Does that make sense? All right. Now we know how to do that already. We have 1 in here, we have -1 in here. I want to make this guy become 0. Pretty easy. I just add the second to the third, right? So I can write here. I can write R2 plus R3, and we do that in R3. The first equation does not change. The second does not change. The last one will be 0, 0, 3, and -3. Okay? All right. So we are almost there. The third equation looks like, I can rewrite this, x minus 2y plus 3z equal to 9, y plus 3z equal to 5, 3z equal to -3. So that's what we got. And let's solve the last equation. We got z equal to -1. Okay. We plug -1 into the second. I got y equal to 5 minus 3z equal to 5 minus 3 times -1, which is 8. And then we plug this into the first one. I got x equal to 9 minus 2y minus 3z equal to 9 minus 3 times 8 minus 3 times -1. We just compute this. We got, this is 16. 9 minus 16 plus 3, which is -4. So finally we already got the solution. X equal to -4, y equal to 8, and z equal to -1. The system has only one solution. Do this again, how we solve this using the matrix form. Okay, so I hope that this method is clear enough, and in my opinion, it looks easier than this way. Given that at the end, we still need to convert the matrix form into the variable form. You see that? But this system is much simpler than the original one. Agree? So if you have any questions, feel free to let me know. Okay, see you in the next video.